Welcome to Linear Algebra Part 7. In this section, we're going to discuss eigenvectors, eigenvalues, orthonormal set, orthogonality in vector spaces, etc. Okay, but mainly these items, these themes. Let's start with the definition of eigenvalues and eigenvectors. So let's say AV is equal to lambda V for some scalar lambda. The scalar lambda is called the eigenvalue corresponding to the eigenvector V. Okay. Eigenvectors do not change direction when multiplied by the matrix. They only scale the matrix itself by lambda, okay? Either to increase the scale or the length of this matrix or vector, decrease the scale or invert it, okay? Invert the direction, the heading. The equation can be rearranged as A minus lambda I multiplied by V is equal to 0. Okay? So A, which is the original matrix, the A matrix, minus lambda, this is the scaling factor, times I, which is the identity matrix, times V is equal to 0, where I is the identity matrix having the same size as A. For a non-trivial solution V different than 0, we require that that of A minus lambda I should be equal to 0. Okay? If V is different than 0, that A minus lambda I should be equal to 0, so that the product of these two gives us 0. This is called the characteristic equation, and solving it gives the eigenvalues lambda. Example, let A equal to 1, 1, 2. The characteristic equation is that of A minus lambda I, which is equal to that of 2 minus lambda 1, 1, 2 minus lambda, the determinant of this matrix. Okay, how did we get this to begin with? So, A minus lambda I is given by matrix A, which is 2, 1, 1, 2, multiplied, minus lambda, which is the scaling factor, multiplied by the identity matrix having the same size as A, which is 2 by 2, 2 rows and 2 columns, which is 1, 0, 0, 1. Okay, if you add them together, so 2 minus lambda here, element by element, 2 minus lambda, 1 minus lambda times 0, which is 1, then 1 minus lambda times 0, 1, and 2 minus lambda times 1, okay? Element by element. So you get here 2 minus lambda, which is equal 2 minus lambda square minus 1, equal lambda square minus 4 lambda plus 3. Example, let A equal to 1, 1, 2. First of all, we start with the characteristic equation, which is that or determinant of A minus lambda I equal determinant of 2 minus lambda 1, 1, 2 minus lambda. How we've gotten that matrix anyway? We start with A minus lambda I, with I being the identity matrix. So A is 2, 1, 1, 2, minus lambda multiplied by the identity matrix having the same size as A, which is 1, 0, 0, 1, or 2 by 2, 2 rows and 2 columns, equal 2 minus lambda times 1, which is 2 minus lambda, then 1 minus lambda times 0, which is 1. Okay, so we're adding element by element. Then 1 minus lambda times 0, okay, so 1 minus lambda times 0, which is 1. Lambda times 0 is 0. And finally, 2 minus lambda times 1, so 2 minus lambda. Then we expand this equation, or this determinant, we evaluate the determinant, and we need to get the equations that come out of it, which are, you have 2 minus lambda square, okay, let me write it on top here, 2 minus lambda square, correct? We multiplied these two, then minus 1 times 1, correct? Which is minus 1. So 2 minus lambda square gives us, let me change the color, 4 minus 4 lambda plus lambda square minus 1. So it is lambda square minus 4 lambda plus 3, which is 4 minus 1. You solve it using the delta or discriminant method, okay, and you get these two roots, lambda equal 1 and lambda equal 3. When placed here, you get, you rewrite them as lambda minus 1 times lambda minus 3 is equal to 0. So the solution, which is the eigenvalues, okay, that render this quadratic equation, which is the characteristic equation 0, are the following eigenvalues, respectively, lambda equal 1 and lambda equal 3. But how we've gotten these two values anyway? So let's solve this quadratic equation, lambda square minus 4 lambda plus 3, which has the form of a lambda square plus b lambda plus c equal 0. The discriminant delta is equal to b square minus 4ac, then lambda 1, the first root, is equal to minus b minus square root of delta divided by 2a, and lambda 2 is minus b plus square root of delta divided by 2a. All right, now delta is equal to b square minus 4ac. B square is 16 minus 4 square 16 minus 4 times ac, which is times 1 times 3. So 16 minus 12 equal 4. So lambda 1 is equal to minus b, or 4, minus square root of delta, which is 2, divided by 2a, a being 1, so 2 times 1, which is 2, which is equal to 1, okay? 2 divided by 2 is equal to 1, so lambda 1 is 1. Then lambda 2 is equal to minus b plus square root of delta divided by 2a, so 4 plus 2 divided by 2, which is 6 divided by 2, or 3. Okay, let me write it here. So lambda 2 is equal to 3. This is how we've gotten the eigenvalues, which are the solution for this equation as we place it equal to 0. That a minus lambda I equals 0. This is how we're getting the eigenvalues. Now, how do we get the eigenvectors? Okay, so for lambda equal 1, so how we're getting the eigenvectors then? For lambda equal 1 and lambda equal 3, we replace lambda in the first equation, which is 2 minus lambda, which is the equation or characteristic equation a minus lambda I. Okay? And we solve the vectors. So for lambda equal 1, let's check what we get. You have the matrix 2 minus lambda 1, 1, 2 minus lambda, which is a minus lambda I, correct? Okay, equal to lambda is 1 in this case. So it is 1, 1, 1, 1. And you multiply it by a vector equal 0. The vector is the one that we will designate as an eigenvector, okay? So the vector v has the coordinate x, y. We need to find x and y in such case. This is how we solve it. So you have 1, 1, 1, 1 multiplied by x, y equals 0. So x plus y is equal to 0 in both equations. Okay, so let's say x, okay, we let x be 1, which is a fixed value. So if x equal to 1, y is equal to minus x, which is minus 1. Okay, so the vector, the first eigenvector is 1 minus 1, because x, the first argument, which is x, is equal to 1, and since y is equal to minus x, y equal minus x equal minus 1. So it is 1 minus 1. This is the first eigenvector. Now let's check the second eigenvector. For lambda equal 3, we place it back in the first equation. So a minus 3i, because lambda is equal to 3, is equal to 2 minus 3, which is minus 1, correct? 1, then 1, and 2 minus 3, which is minus 1. Okay, multiplied by vector v to be determined, which has coordinates x and y is equal to 0. So the first equation is minus x, okay, element by element, remember, plus y is equal to 0, and x minus y equal to 0. Okay, in both cases you have x is equal to y. So we assume x is equal to 1. It needs to be chosen by us, one like a specific value, special value. So for x is equal to 1, y is equal to x is equal to 1. And hence the eigenvector in such case for lambda equals 3 is 1, 1. These are the two eigenvectors we came up with. Given a square matrix A that exists in R and N or C and N, the characteristic equation is the polynomial equation obtained by setting the determinant that of A minus lambda I is equal to 0, where I is the n by n identity matrix, lambda is a scalar, the unknown. Okay, you have the solutions, lambda are the eigenvalues of A. The equation AV is equal to lambda V can be rearranged into A minus lambda I times V, as we've seen already. So you get the determinant to solve the equations for which values of lambda this becomes eliminated. Okay, this equation becomes 0. This is the condition for the existence of eigenvalues, which is that of A minus lambda I should be equal to 0. Finding the eigenvalues. So you start with a square matrix A within R and N, compute the characteristic polynomial P of lambda, which is that of A minus lambda I, determinant of A minus lambda I. You solve the characteristic equation that A minus lambda I is equal to 0. You find the solutions for lambda, or the values of lambda for which this becomes equal to 0. The equations become solvable, or like they are rendered 0. For which values of lambda? These values for which the equations become 0 are the eigenvalues of A, which are the solutions lambda. Okay, finding the eigenvectors. So for each eigenvalue lambda, you substitute lambda into A minus lambda I for the different solutions. Okay, so you solve the homogeneous system to find the eigenvectors. So for lambda equal 1, you replace it, or you place it back in A minus lambda I to find the first set of eigenvectors. Okay, then for the second value of lambda, you also get the other eigenvectors. So, and the set of all eigenvectors obtained plus the 0 vector for lambda is called the eigenspace of lambda. Diagonalization of matrices. Okay, definition. A square matrix A within R and N dimension is diagonalizable if there exists an invertible matrix P and a diagonal matrix D such that A is equal to P times D times P minus 1. Okay, so D is a diagonal matrix containing the eigenvalues of A. The columns of P are the corresponding eigenvectors for A. Notice something. This resembles the transfer of base, okay, like the transfer of coordinate system for a matrix from one base to another. So it's so similar to that. Now, when is a matrix diagonalizable? So if A has n linearly independent eigenvectors, then A is diagonalizable, meaning that the number of vectors should be equal to n that are independent eigenvectors. 2, a sufficient condition. If A has n distinct eigenvalues, then it is diagonalizable. 3, if eigenvalues have multiplicity greater than 1, then we must check the dimension of eigenspaces or geometric multiplicity. Steps to diagonalize a matrix. First, find eigenvalues of A. Solve characteristic equation, in other words. Then find the eigenvectors for each eigenvalue by replacing lambda with the different roots that we found. Okay, we find the eigenvectors corresponding to these eigenvalues. Then check if you have n linearly independent eigenvectors. If yes, the matrix is diagonalizable. If no, matrix is not diagonalizable. Okay, so you construct P equal V1, V2, Vn matrix eigenvectors. D equal diagonal of lambda 1, lambda 2, lambda n. Example, let A equal 4, 1, 2, 3. Let us find the eigenvalues, then the eigenvectors, and other things that need to be found. So, eigenvalues. So, we need to solve A. Okay, you get 4, 1, 2, 3. Let us solve it. A minus lambda I equal to 4 minus lambda 1, 2, 3 minus lambda. Okay, we get the determinant for this A minus lambda I, okay, which is equal to 4 minus lambda multiplied by 3 minus lambda minus 2 equal to 12 minus 4 lambda minus 3 lambda plus lambda square minus 2. Okay, so 12 minus 2 is 10 minus 7 lambda plus lambda square. Okay, we need to get the roots based on this equation. So by evaluating the roots using the discriminant method, you get lambda 1 is equal to 5, lambda 2 equal 2. Okay, now for lambda equal to 5, lambda 1 equal to 5, let's get A minus lambda I in such case, which is A minus 5I equal 4 minus 5, 1, 2, and 3 minus 5 equal minus 1, 1, 2, and 3 minus 5, which is minus 2. So let's get the solution for, okay, so we multiplied by a v vector which is designated by v equal x, y, and we need to find the coordinates for that v by solving this equation. So minus 1, 2, 1 minus 2 times v equals 0, which is, again, v is x, y. So minus x plus y is equal to 0, which is x equal y, and 2x minus 2y is equal to 0, so also 2x equal to y or x equal y. So x equal 1, for x equal 1, you have also y is equal to 1, okay? And this is the first eigenvector, x equal 1, for x equal 1, y equal 1, so 1, 1 is the first eigenvector. Now, for lambda equal to, the same concept, so a minus 2I gives us 4 minus 2, 1, 2, 3 minus 2, which is 3 minus lambda, but lambda is equal to, so 2, 1, 2, 1. Okay, and you multiply that by the vector of having coordinates x and y to be found, equal, we place it equal to 0, so 2x plus y equals 0, so yeah, y equal minus 2x, so if x equal 1, y equal minus 2. So the eigenvector, the unique vector, is 1 minus 2. Now we need to construct P. P is equal to, you place the different eigenvectors as columns, respectively, within the P matrix. So P is equal to 1, 1, 1 minus 2. Now, we need to construct D also. So what is D? D is 5, 0, okay, 0, 2, which is basically lambda 1. Okay, D is lambda times the identity matrix, okay, big lambda, meaning that the first solution multiplied by the first row, second solution multiplied by the second row, which is 5, 0, correct? 5, 0, and 0, 2. This is lambda 1 here, and this is lambda 2. Okay, so A is equal to P times D times P minus 1. Okay, actually we get the solution, okay, as being P times D times P minus 1, or the inverse of matrix P. Now, geometric versus algebraic multiplicity. Algebraic multiplicity, or AM, is the algebraic multiplicity of an eigenvalue lambda, okay, or the number of times lambda appears as a root of the characteristic polynomial. In other words, if P of lambda is equal to determinant of A minus lambda I, which is equal to 0, has a factor lambda minus lambda 0 to the power of k, then the algebraic multiplicity of lambda 0 is equal to k. Okay? Like the duplicate of roots, how many, the number of times lambda appear as a root of the characteristic polynomial. Now, geometric multiplicity, GM, the geometric multiplicity of an eigenvalue lambda is the dimension of its eigenspace. Okay, so the eigenspace is defined by E lambda V different than 0 of A minus lambda I times V equal to 0. So it is the number of linearly independent eigenvectors, simply. Okay, the eigenspace is the number of linearly independent eigenvectors corresponding to lambda. Like in the previous example, we had two eigenvectors, 1, 1 and 1 minus 2. So the eigenspace is equal to, because we had two linearly independent eigenvectors. This is what we call here in this context the geometric multiplicity. Okay, now when you have a root which is a square root, meaning that lambda minus 2 to the power of 2, so you have a recurrence of the same root, meaning the same root being repeated over and over because it's multiplied multiple times. In such case, it is the same root, but it is a square root. Okay, so let's say lambda minus 3 to the power of 2. So lambda equals 3, it's occurring multiple times. In this case, or in such case, it's occurring twice. Hence, the algebraic multiplicity of lambda 0 is equal to, so k equal to. Relationship between AM and GM for every eigenvalue lambda. GM lambda is greater than 1, less than the algebraic multiplication. Okay, the geometric is between 1 and the algebraic multiplication. If Gm and Am for all eigenvalues and the sum of Ams is equal to n, which is the size of matrix, then the matrix is diagonalizable. If Gm, Am for some eigenvalues different than Am, okay, the matrix is not diagonalizable if Gm is different than Am. Okay, so it's called defective. Example, distinct eigenvalues. So A equal 4, 1, 2, 3. The eigenvalues, as we've seen before, are lambda equal 5 and 2, both distinct. So Am of 5 is equal to 1 when you place 5 within the A minus lambda. Am of 2 is equal to 1. Gm of 5 equal 1. Gm of 2 equal 1. So Gm is equal to Am, which means this matrix is diagonalizable. Now let us break it down and make it more comprehensible because it seemed to be ambiguous so far. For lambda equal 5, at first, lambda equal 5 occurs only once. We don't have a double root, okay, like two roots that happen to be, or a square root that happens to be lambda equal 5. You only have one lambda equal 5 and one lambda equal 2. Hence, the algebraic multiplicity of both 5 and 2 is only 1. Like you don't have, for example, lambda minus 3 squared. In such case, lambda equals 3 occurs twice. As an example, you have only one lambda equal 5 and one lambda equal 2. No double roots. In such case, so Am5 is 1 and Am2 is 1. Now, for the geometric multiplicity for 5, for lambda equal 5, you only have one unique eigenvector, so it is equal to 1. For Gm of 2, the geometric multiplicity of 2, you also have one unique eigenvector, not more than that. So Gm is equal to Am, hence this matrix is diagonalizable. Repeated eigenvalues. Okay, or eigenvalue. If you have only one that is repeated, let's say you have the matrix B equal to 1, 0, 2. The characteristic polynomial would be lambda minus 2 squared. Okay, how did we get that? We solved the characteristic equation, which is determinant of B minus lambda I, okay, which is 2, 1, 0, 2 minus lambda times the identity matrix, which is 1, 0, 0, 1. So you end up with 2 minus lambda 0. Okay, you have 2 minus lambda, and here you have 1. Okay, 1 minus 0, so 1. Then 0, 2 minus lambda. Let us find the determinant for B minus lambda I, which is the following. So it is equal to 2 minus lambda square, and this one is annihilated when you multiply the second, like this diagonal. Okay, so 2 minus lambda square, which is, in other words, okay, so the root is lambda equal 2. However, what we have here is the power of 2, meaning that there's a repetition of lambda twice. So lambda equal 2, this is a double root, okay, since here the power is 2. Okay, so you have lambda 1 equal 2 and lambda 2 also equal 2. So you have one double root. In other words, this root is repeated twice. Now, so the characteristic polynomial is lambda minus 2 squared, lambda equal 2. This is the eigenvalue. Since it is repeated, since you have it twice, and since like the power of this is 2, hence the algebraic multiplicity of lambda equal 2, Am2, is equal to, since the root repeats twice, okay, due to the fact that we have, again, this power here. power of 2. Okay, so you have lambda equal to twice. Now solve b minus 2i times v equals 0. So b minus 2i, which is lambda that we found, lambda equal to, so what would be the matrix? B minus 2i, or b minus lambda I for lambda equal to. In other words, you have 2, 1, 0, 2 minus lambda multiplied by I, 1, 0, 0, 1. So 2 minus 2 is 0, 1 minus 0, 1, because minus 2 times 0 is 0. Okay, then 0 and 2 minus 2, which is 0. Okay, 2 minus 2 times 1. So you end up with this matrix. Okay, now you have, let's multiply row by column. The second one won't matter because it's 0. So 0 times x plus 1 times y, which is y equal 0. Now x is undetermined, but we assume that x is equal to 1. So the eigenvector is 1, 0. Okay? So this is one eigenvector, hence the geometrical multiplicity of 2 is equal to 1, since we have only one eigenvector. Gm is less than am. They are not equal, in other words. So as a result, the matrix B is not diagonalizable. It's only diagonalizable when Gm is equal to Am, equal to, in such case, 2, which is the number, the size of the matrix. Okay, n by n, this is, or like n by m matrix, where n equal m equal to the number of rows is equal to the number of columns equal 2. As a takeaway, algebraic multiplicity again is how many times the eigenvalue repeats itself in the characteristic polynomial or the power of the polynomial that we get. Okay, so 2 minus lambda in the former example was to the power of 2. It means that lambda equal 2 is repeated. Okay, it is twice the root of, or the solution for that of b minus lambda I. Now, second, geometric multiplicity is how many independent eigenvectors correspond to that eigenvalue. As we've seen in the former example, we only got one eigenvector versus two, versus, yeah, the AM algebraic multiplicity was 2, meaning that you had a double root. So the condition for diagonalization is that Gm, the geometric multiplicity defined by the number of eigenvectors that are independent, should be equal to the algebraic multiplicity, which is how many times the eigenvalue repeats itself. Okay, so if you have a root that is, let's say, for example, lambda minus 1 to the power of 3. In such case, the algebraic multiplicity would be 3, since lambda is equal to 1 is a root repeated 3 times. Okay, like you can write it as lambda 1 equal 1, lambda 2 equal 1, and lambda 3 is equal to 1. So Gm should be equal to Am for all eigenvalues, so that the matrix would be diagonalizable. Find the eigenvalues and eigenvectors of the following matrix. Okay, you can pause the video, try to solve it, and then come back. Let's start. At first, we need to evaluate that of A minus lambda I, as usual. Okay, so you simply evaluate the determinant of 2 minus lambda 1, 0, 3 minus lambda. Okay, A minus lambda I is simply obtained by subtracting all the elements of the diagonal, only the diagonal without the other elements, by lambda. So starting from the first one, you have 2 minus lambda. Then the second one within the diagonal, I'm stating 3 minus lambda, and the other elements remain the same. Okay, after that, to evaluate the determinant, as usual, you multiply these two together, minus 0 times 1, so it is 2 minus lambda times 3 minus lambda. Okay? And we have immediately the roots for which this determinant becomes 0. Okay? So this becomes 0 for simply either lambda equal 2, because 2 minus 2 is 0 multiplied by 3 minus lambda, it renders it 0, or lambda equal 3. Okay, so you simply place, okay, so 2 minus lambda is equal to 0, then lambda equal 2, that's the first eigenvalue, and 3 minus lambda equals 0, so lambda equal 3. That would be the second eigenvalue. So lambda equal 2, lambda equal 3. Let us evaluate for each lambda the eigenvectors. Okay, now for lambda equal 2, what we obtain is, so 2 minus lambda and 3 minus lambda, okay, so the vector becomes, you simply place lambda equal 2 within the original A minus lambda I matrix, okay, so you get 0, 1, 0, 1. And let us assume the vector v or x, big X, is equal to xy, so you place them next to each other. So we are trying to solve A times x is equal to 0 to find the values of x. Okay, so 0, 1, 0, 1, xy is equal to 0, 0. In other words, x times 0 plus y is equal to 0. So you have y is always equal to 0. Now x is not solvable, but you assume that x is equal to 1. And we get this eigenvector, which is v1 is equal to 1, 0. That's the first eigenvector. Okay. Now we need to get the eigenvector for lambda equal 3. For lambda equal 3, remember what was the matrix, the original one, 2, 1, 0, 3. So 2, 1, 0, 3. This is A minus lambda I, correct? So lambda is 3. So 2 minus 3, 1, 0, and 3 minus 3. Minus 1 here, 1, and 0, 0. This is A minus lambda I for lambda equal 3. So minus 1, 1, 0, 0 multiplied by x, y to get the values of x and y equals 0, 0. So first equation is minus x plus y equals 0. Hence, x is equal to y. If we consider, and of course for the second one, doesn't matter because it renders everything 0 for the second row. So y is 3 and we consider it 1. If x equal y, then x equal 1, y equal 1, and the eigenvector is v2, 1, 1. So for lambda equal 2, the basis is, which is the first eigenvector, it is 1, 0. Okay, the vector we obtained in the previous page. For lambda equal 3, the basis is 1, 1, which is v2. Therefore, A is diagonalizable. Okay, now why? Because it's equal to the basis is 1 by 1. Okay, both for lambda 2, lambda 3, and you have also so yeah, let's go back to the algebraic multiplicity and the geometric multiplicity. Okay, geometric multiplicity define the number of eigenvectors for each solution, okay, for each lambda value, for each root. So gm of 2 is equal to 1, and gm of 3 is equal to 1. But also on top of that, the algebraic multiplicity, which is simply the number of roots, okay, if the root is being repeated, the algebraic multiplicity would be equal to the number of repetitions. So here we have only one citation, one root for 2 and 3. So am of 2 is equal to 1. You don't have a double root. You don't have a repetition. Okay? And also am of 3 is equal to 1. So am is equal to gm equal to 1 for both roots, for 2 and 3. Therefore, A is diagonalizable. Okay, this is how we draw the conclusion. So, now, A is given by P minus 1, which is the inverse of P times D times P. Okay, now, P is actually the set of the two vectors V1 and V2. This is P, okay? P is equal to V1 here and V2 here. The vectors, the eigenvectors actually. The first vector is 1, 0. The second eigenvector is 1, 1. This is P, okay? P1 is the inverse of P, which is equal to 1 divided by the determinant, which is 1, multiplied by, okay, you swap 1 and 1, but it doesn't matter, they are the same. And you multiply this second diagonal by minus, so you have 0 minus 1. So P minus 1 is actually 1 minus 1, 0, 1. Okay, and D, what is D? D is, you place lambda 1 and lambda 2 on the diagonal. Okay, so lambda 1, which is 2, the first root, lambda 2 is 3, the second root, and the remainder is 0. So if you multiply P minus 1 times D times P, okay, you recover what? The original matrix. This is what diagonalization means. Another one, find the eigenvalues and eigenvectors for the following matrix: B equal 1, 2, 0, 0, 1, 0, and 0, 0, 4. Pause the video if you want to try it yourself first. Let's continue. Finding eigenvalues, which is resolving that of A minus lambda I. Here, in this case, instead of A, you place B, as simple as that. Okay, but the same formula, it's still the same. So for all the diagonal elements, okay, you subtract them by or from you subtract lambda from them, so you get 1 minus lambda, 1 minus lambda, and 4 minus lambda, and all the other elements within the matrix remain the same. So which is equal to, let's evaluate the determinant. It is 1 minus lambda, okay, multiplied by 1 minus lambda times 4 minus lambda, and this is 0, it doesn't matter. Then you have 2, okay, minus 2 here, multiplied by 0 minus 0, so it doesn't matter, okay, it cancels out. Then 0 multiplied, whatever multiplies 0 becomes 0. So we are left with 1 minus lambda, 1 minus lambda, and 4 minus lambda, which gives us lambda equal 1. And notice something, this is a square root, okay, so this is repeated twice. So 1 minus lambda is simply 1 minus lambda square, because it's multiplied twice. You notice here, this is the geometric, this is the algebraic multiplicity of this lambda, and it's equal to 2, not 1. Okay, so the algebraic multiplicity, which defines or determines how many times the same root is repeated, for 1 minus lambda, for lambda equal 1, in other words, okay, you have 1 minus lambda square, so you have 2. AM, algebraic multiplicity of 1, is equal 2. Okay, and multiplied by 4 minus lambda. Here, the second root is lambda equal 4. Its algebraic multiplicity is 1, because it's occurring only once. Okay, for lambda equal 1. So we place back lambda in this equation, A minus lambda I. So you get 1 minus lambda, 1 minus lambda, 4 minus lambda, which is 0, 0, 3. Okay, and for the other values, you have 0, 0, 0, you have 2, 0, 0. Okay, let us multiply it by the vector x having coordinates x, y, z, and find out what that vector should be like. Okay, so let's resolve it. X is 3, we consider it 1. Okay, so let me manually check it. You have z, 3z is equal to 0, okay, in the third row. So z is equal to 0. You have here the 3, okay, 3, 0, so it's irrelevant. Now in the first row, you have 0 times x plus 2 times y plus 0 is equal to 0. So 2y is equal to 0 and y equal 0. Z equals 0. And we consider x is equal to 1. Hence, the eigenvector would become 1, 0, 0. For lambda equal 4, we replace b minus lambda I with b minus 4i. So you have 1 minus 4, 1 minus 4, and 4 minus 4, which is minus 3, 0, and other elements remain the same. X is given by x, y, z. We're going to find this x vector. So minus 3 to 0, 0 minus 3, 0, and 0, 0, 0 times x, y, z is equal to 0, 0, 0. We're going to find x, y, and z. Okay, so first equation is minus 3 times x plus 2y plus 0 is equal to 0. That's the first equation. Then you have 0 times x minus 3y plus 0z is equal to 0. Then 0, 0, 0. So we have y is equal to 0. X is equal to, minus 3x equal to minus 2y. So x is equal to 2/3 y. Since y is equal to 0, so x is equal to 0 as well. Z is free, so we take it as z equal 1. So V2 is equal to 0, 0, 1. As a result, so what we have so far, AM1 is equal to, so it's repeated twice, AM4 is equal to 1. As for the geometric multiplicity, GM of 1 gives us 1 vector, and GM of 4 gives us also 1 vector. Now, GM1 is different than AM1, so you have GM1 is 1, different than 2, which is AM1. Hence, this vector or this matrix is not diagonalizable. Orthogonal or orthonormal sets. Okay, orthogonal vectors, two vectors uv within Rn are orthogonal if their dot product is 0. So example 1, 0 and 0, 1 are orthogonal in R square. Why? Because x times x, x1 times x2 plus y1 times y2, which is the dot product, is equal to 0 plus 0, which is 0. Orthogonal set, a set of vectors v1, v2, vk is orthogonal if every pair of distinct vectors is orthogonal. vi, vj is equal to 0 for all I different than j. If none of the vectors are the 0 vector, then an orthogonal set is automatically linearly independent. Okay? Orthonormal set. An orthogonal set is called orthonormal if, in addition, each vector has unit length. So vi is equal to 1, a unitary length, for all I. That is, vi.vj is equal to 1 if I is equal to j, and 0 if I is different than j. Example in R3, the standard basis. So you have 1, 0, 0, 0, 1, 0, and 0, 0, 1. If we multiply any of these vectors with the other, you get 0. They are at first orthogonal. Now, actually for I equals j, I think, the dot product is 0. So vi times vj, so 1 times 0 becomes 0. Otherwise, if I is different than j, so first row in the first one and second row in the second one, okay? So the product would be 1. The point is, if they have unitary length, then on top of being orthogonal, which means that the dot product of any two of these vectors is 0, if on top of that they have unitary length, they are like unitary vectors, like we see here, 1, 0, 0, 0, 1, 0, 0, 0, 1, then they are orthonormal. The set itself, rather, is orthonormal. Properties of orthonormal sets. So if Q1 all the way to Qk is orthonormal, any vector x in their span can be expressed as x equals C1 Q1 plus C2 Q2 plus 3 points plus Ck qk, where coefficients are found easily by ci equal x times qi. Second, the matrix Q is equal to Q1, Q2, Qk is actually orthogonal. So Qt, the transpose of Q multiplied by Q, gives you back the identity. Such matrices are called orthogonal. So the transpose of the Q matrix multiplied by Q gives us back the identity. Projection of a vector onto another vector. Okay, let UV exist. These are two vectors existing in Rn with u different than 0. The projection of V onto u is the following. It is, so projection of V onto u is V dot u divided by u dot product u multiplied by u vector. Okay? So because the dot product gives us a scalar, a like finite value, not a vector. So it is V dot u, which gives us a value, divided by u dot u gives us another value, multiplied by the u vector. This gives us the projection of V onto the u vector. This gives the component of V in the direction of u. Okay? It gives the component of V. So the error vector, also another concept, E equal V minus projection of VU, V, okay, is orthogonal to U. Now, to give you like a visualization, so let's say this is the V vector and this is the U vector. What does it mean, the projection? This is when V is projected onto U, okay, what its value would be like. This is what we mean by the projection of V over U. So let's call it V prime. That would be the projection. Now, mind you that it would get it would have the same direction as U, okay, but a different length. It's like the shadow drop of V over U when the sun is above it, so to speak. Projection onto a subspace. Let W be a subspace of Rn with bases U1 all the way to UK. The projection of V onto W is the unique vector P existing inside of W such that V dash P is orthogonal to W. Okay? Projection with orthonormal basis. If Q1, Qk is an orthonormal basis of W, then projection is easy. So projection of V, okay, projection of W over V, or V over W, I'm sorry, is equal to V dot Q1 multiplied by Q1 plus etc. Okay, here it's just a concept. I did not get deep into this one. So this is called the Fourier expansion of V in the subspace W. Okay. Matrix form of projection. Let's say you have U containing U1, U2 all the way to UK. It contains a basis or basis vectors of W. If basis is orthonormal, so P is equal to U times U times the transpose of U. Okay, P being the projection, so projection of V over W is equal to P V. If basis is not orthonormal, P would be equal to U times transpose of U times U, the inverse of all of that, multiplied by transpose of U. Okay, so you can memorize them as formulas. Okay, doesn't matter, like not necessary to go deep into these things. I've gone a little bit deeper than necessary, depending on your schedule or your curriculum, of course. Okay, as an example, so you have V equal to 3. We need to project V onto U. Okay, so let us retrieve the formula. The projection of V onto U is given by V dot U, which is the dot product of P and U, divided by U dot U, multiplied by the U vector. So V dot U is 2 times 1 plus 3 times 1. So 2 plus 3, which is 5. Correct? Let me get the pen. Then you have u dot u is 1 times 1 plus 1 times 1, which is, or 1 squared plus 1 squared, which is 2. So you get 5 divided by 2 multiplied by u, okay, which is the vector here. Okay, so what do you get? You get 5 over 2, 5 over 2, that would be the vector. Or written in a different way, 2.5, 2.5. This is like the final vector. Okay, the error vector, let us retrieve the formula. So error vector is equal to v minus projection of v over u. What is v? It is 2/3 minus 2.5, 2.5, meaning how different is the projection from the original vector. This is what the error is referring to, okay? So it is 2, 3 minus the projection 2.5, 2.5 is equal to, you subtract element by element, minus 0.5, 0.5. Check u dot e, the dot product between u and the error vector. So it is minus 0.5 times 1 plus 0.5 times 1 equals 0. Okay, you see, as we evaluate the vector, it is equal to 0. Hence, this is an orthogonal vector. So this means that u is in fact, actually, I'm sorry. This means that in fact it is the projection which is 90-degree orthogonal to the projection is 90-degree orthogonal to the u vector. Again, as a reminder, it is the projection of v against u. So when we get the dot product between the u vector and the error vector, we should obtain 0, which confirms that it is orthogonal. All right, let us talk a little bit about the Gram-Schmidt orthogonalization. Okay, the Gram-Schmidt process takes a set of linearly independent vectors, v1, v2, vn, and produces an orthogonal or orthonormal set of vectors given by u1, u2, un, or e1, e2, en that span the same subspace. Starting, okay, you start with u1 equal v1, then for k equal 2, 3n, we evaluate uk equal vk minus the sum. Okay, this is how we get the different vectors. So uk, for k equal 1, it would be u1, v equal v1, minus the sum from j equal 1 to k minus 1. Okay, so if k equal 2, that would be from 1 to 1, okay? Of vk uj divided by uj uj, okay? The vectors multiplied by uj. I think this is a dot product here. I haven't checked it. Okay, I think, yeah, I assume it is a dot product. So this removes the components of vk along earlier vectors, leaving it orthogonal. If you want an orthonormal set, ek is equal to uk divided by the norm of uk, or the length of uk. So let's suppose v1 is equal to 110, v2 is equal to 101. First vector would be u1 is equal to v1 equal 110. Orthogonize v2, which is u2 is equal to v2 minus v2 u1. Okay, so u2 is equal to v2 minus u2 v2 u1 divided by u1 u1 times u1. So it is, yeah, we're multiplying v1 and v2, I assume. Okay, 1 times 1, then 0 times 1, then 1 times 0, which is 1. This is v1, v2. Okay. Yeah, it's all a little bit confusing. Okay, so you continue. So v1, v2, then v2, u1. Okay, what is u? That is v2, 101 times u1, which is 110. Okay, you multiply them together, gives you 1. Then u1, which is 1 squared plus 1 squared plus 0 squared equal 2. So u2 would be, okay, you evaluate the entire thing. So going back to the formula, it is v2 minus this quantity times u1, which is 101. That's v2 minus 1 half 110 equal 1 half minus 1 half 1. Okay, so u1 is orthogonal to u2. Okay, so normalize. E1 is u1 divided by the length of u1, which is 1 divided by square root of 2 multiplied by 110. Okay, E2 is u2 divided by the modulo or the length of u2 equal 1 divided by square root of 6 times 1 minus 1, 2. Okay, so it is, yeah, basically it can be written in a different way, like it is 1 divided by the modulo of u2 or the length of u2 times the u2 vector. So it is 1 divided by square root of 6, which is, yeah, modulo of u2 is square root of 6, which is, yeah, square root of 1 half square plus minus 1 half square plus 1, you obtain 6. Then, okay, you divide 1 over square root of 6 and you multiply with u2, with the u2 vector, okay, which is 1 minus 1, 2. Okay, the orthonormal set is then 1 divided by square root of 2, 110. And the second one is 1 divided by square root of 6, 1 minus 1, 2. We need to stick to the formula, okay? You stick to the formula. Let us break it down again. So you have u2 is equal to v2 minus v2 scalar product, or I'm sorry, dot product u1 divided by u1 dot product u1 multiplied by u1, okay? So the first vector you have v1 is 110. It is supposed within, like, inside the exercise. v2 is 101. Okay, they are suggested. You have u1 is equal to v1 equal to 110. We start with that. Then u2 is equal to v2, okay, minus v2 u1. Okay, this is v2, remember. Okay, so minus v2 dot u1 divided by u1 dot product u1 times u1. This is how you get the second vector. You compute v2 u1. Okay, you follow by the formula. Okay, I might have made some mistakes. You end up with this orthonormal set at the end. Least squares problem. Okay, definition. We want to solve an overdetermined system of linear equations. Let's say ax is approximately equal to b, where A is an m by n matrix with m greater than or equal to n. More equations than unknowns. This is the problem that we have here. And B belongs to Rm. So usually there's no exact solution. Instead, we look for x that minimizes the error, okay, which is minimum ax minus b to get the value of x that minimizes, again, the error. This is called the least squares solution. Geometric interpretation: ax lives in the column space of A. B may not be in that space, okay, which is the second side of the equation. The solution is the point in col A closest to B. Equivalently, projection of B onto col of A. Okay, so the solution is the projection of B over the column of A. Normal equations approach. So the condition for the projection is AT multiplied by AX minus B is equal to 0. This gives, or this becomes, transpose of A multiplied by AX minus transpose of A times B is equal to 0, or AT-AX is equal to AT-B. So ATA is square matrix n by n. Its size is, so if A has full column rank, ATA is invertible. Solution: ATAX is equal to ATB. Okay, now here we need to introduce something called QR factorization. It's better to see it within an exercise to make it easier, okay? Or QR decomposition, A is equal to Q times R, QT times Q is equal to I in this case, okay? And R is the upper triangle, triangular matrix. So we're trying to triangulize, okay? So, and then we get the minimum of AX minus B. Okay, let's try an exercise to make it much easier. Example, solve in least squares sense. A equal 1, 1, 1, 1, 2, 3, and B equals 6, 0, 0. Okay, we need to compute AT times A, which is the transpose of A times A, okay, and then transpose of A times B. So you get, let us check it out. The transpose of A is simply you transform, like you flip the column into a row, 1, 1, 1. Second column becomes another row, 1, 2, 3. That's AT, okay? That's the transpose of A. And then you multiply it by A, which is the original matrix, which is 1, 1, 1, and 1, 2, 3. And you obtain this square matrix. By the way, again, notice that it will have the number of lines of the first matrix and the number of columns of, actually the number of lines of the first matrix and the number of columns of the second matrix, which is 2 by 2, which gives us 3, 6, 6, 14. This is the product, okay? Why? Because you see here, so for the first element, you have 1 times 1 plus 1 times 1 plus 1 times 1 equals 3. This is A11. Then you have, for example, here the second row, second column, 1 times 1 plus 2 times 2 plus 3 times 3, which is 4 plus 9 plus 1, or 14. Yeah, this is 14, okay? Now, AT times B, we multiply AT times B, which is the transpose of A, which is 1, 1, 1, 1, 2, 3, times B, which is 6, 0, 0, and you get 6 plus 0 plus 0, that's the first. Then you have 6 times 1, okay, plus 0 plus 0. So 6, 6, okay? Yeah, 1 column and 2 rows, okay? So the number of column based on that, it would be based on the second matrix we're multiplying, and the number of rows based on the first. So 6 by 6, okay? Like 1 row, 1 column, 2 rows, okay? 6, 6. From the first equation, okay, like if we place them next to each other, you get 3, 6, 6, 14, which is AT times A, multiplied by a variable x1, x2, which is an unknown vector, is equal to 6, 6. Okay, so let me make it clearer. Let me clear the ink. So you have ATA gave us this matrix and ATB gave us 6, 6. So you place them next to each other as, yeah, the first part should be multiplied by vector x1, x2 is equal to 6, 6. From the first equation, okay, let's get the equation. So 3x1 plus 6x2 is equal to 6. Equals 6. The second equation is 6x1 plus 14x2 equals 6. So from the first equation, you factor out the 3. So you get x1 is equal to minus 2x2. You substitute x1 in the second equation. So you place it back in this equation, the second one. So we get x2 is equal to minus 3 and x1 is equal to 8. So the final answer is x equal 8 minus 3. I hope it's clear, okay? So you place ATA on the left, multiply it by an unknown vector for which we need to find the argument. given by x1, x2 in this case, because we're talking about 2 by 2 size, equal to ATB, which is like the constant part of the equation, of the system rather. So 6, 6, you get 3x1 plus 6x2 equals 6. That's the first equation. Okay, we can factor out 3. So if we divide the entire equation by 3, you get x1 plus 2x2 is equal to 2, correct? Then you move 2x2 to the right, so x1 is equal to minus 2x2. And this value of x1, I place it back within the second equation, which is 6x1 plus 14x2 equals 6. So we get both x1 and x2. And this is your final answer, or your vector, which is called or defined by the least squares solution. QR factorization decomposes a matrix A into two matrices, A equal Q times R, with Q is the orthogonal or unitary matrix given by Q, which is has a property that is the transpose of Q multiplied by Q gives you back the identity vector, and R is the upper triangular matrix, which means that it is the matrix for which every element below the diagonal is 0, and otherwise it can be different than 0. Okay, so only the values below the diagonal are 0. As for the ones above it, they can be anything. Okay, it's widely used in solving least squares problems, numerical linear algebra, and eigenvalue computations. Connection with Gram-Schmidt: if A is an m by n matrix with linearly independent columns, A equal A1, A2, An, applying Gram-Schmidt to its column gives an orthonormal set of vectors Q1, Q2, Qn. These form the columns of Q. Okay, these would be the columns of Q. Coefficients Rj, Rij that describe how each Aj is built from Qi's. These form R, these coefficients. The procedure: step 1, Gram-Schmidt on the columns of A. So Q1 is equal to A1 divided by the modulo or the size of A1. Q2 is equal to A2 minus Q1. Yeah, it's a little bit complex process. Okay, never mind. It might be much easier within the exercises for you to comprehend. Okay, let's move to practice. So let A equal to 1, 1, 0, 1, 0, 1. Okay, compute Q1. So you have, at first, A1 is the first column designated by 1, 1, 0, and its size or its length is given by A1 equal to square root of 1 square plus 1 square plus 0 square, which is square root of 2. So Q1, what is Q1? Q1, as a reminder, is A1 divided by the size of A1, which is rewritten as 1 divided by A1 to make it clearer for you, divided by A1 modulo or the size of A1 multiplied by A1. The size of A1 is square root of 2, so this gives us 1 divided by square root of 2 multiplied by 1, 1, 0, which is the original vector A1. Now, compute Q2. Okay, so you have A2 is the second column designated by 1, 0, 1. So projection on Q1, you have here Q1t A2 times Q1. So this is a formula that we should memorize. The transpose of Q1, what is Q1? Okay, so it is 1 divided by square root of 2, and this column becomes a line, which is 1, 1, 0, multiplied by A2, which is 1, 0, 1, and then you multiply it by Q1. Okay? So projection on Q1, you need to memorize this formula. It is given by transpose of Q1 multiplied by A2, then together multiplied by Q1. Transpose of Q1, this is Q1, its transpose is 1 square root of 2 times 1, 1, 0. So the column becomes a row, as simple as that. Multiplied by A2, which is A2 is given by 1, 0, 1. Okay, so it is the vector 1, 0, 1, the second column. So you multiply, let us remove this excess here. Now, going back to the pen, okay, multiplied by A2, which is 1, 0, 1, and times Q1, which is the original Q, okay, this is Q1, okay, you multiply again by 1 times square root of 2 times 1, 1, 0. So it gives you, okay, 1 divided by square root of 2, 1 plus 0 times Q1 equal 1 divided by square root of 2 of Q1. Okay, now U2 is equal to A2 minus 1 divided by square root of 2 Q1, okay, which is 1, 0, 1 minus 1 half. You get this one. To normalize, okay, so you have U2 is like the size of U2 is square root of 1 half square plus minus 1 half square plus 1 square, which is 1 fourth plus 1 fourth plus 1 equals square root of 3 divided by 2. Now Q2, okay, so this is Q2 is equal to U2, which is this vector divided by square root of 3 divided by 2, which is, we are normalizing, okay, which is the size of U2. This gives you again Q2. Okay, now the big Q is the set of all these vectors that we obtained. Okay, so you have, what do we have here? 1 square root divided by square root of 6 minus 1 divided by square root of 6 and 2 divided by square root of 6, which is Q2 to the right, and to the left you have Q1. What is Q1? You go back, and I understand it's hard to memorize them. Okay, you need to practice in this case. So going back to Q1, it is 1 square root divided by square root of 2 of 1, 1, 1, 0. Okay, so which is also can be rewritten because you multiply the outside argument to the inside. So it is 1 divided by square root of 2, then 1 divided by square root of 2, and finally 0. Now, R is given by, okay, what is R? You have square root of 2, which is, this argument, and square root of 3 divided by 2, and you have 1 divided by square root of 2 and 0. Okay, so these are the two arguments for R. This is how, actually, how did we build R? How did we get R? R is equal to the transpose of Q multiplied by A. What is the transpose of Q? Transpose of Q, you simply modify or transform the column into row. Each column becomes a row, so 1 divided by square root of 2, 1 divided by square root of 2, and 0. Then the second column becomes a row. 1 divided by square root of 6, 1 divided, minus 1 divided by square root of 6, and 2 divided by square root of 6. And you multiply them by A, which is, where is A anyway? A is the first matrix, 1, 1, 0, 1, 0, 1. So 1, 1, 0, 1, 0, 1. And this is how we ended up with R, which is square root of 2, 0, 1 divided by square root of 2, square root of 3 divided by 2. Again, I understand it is the hardest part so far within this entire course, but you need to practice in order to make it a little bit simpler. Let's do some practice right now, and if you want to try at them yourself first, you can pause the video before continuing to the solution or proceeding to the solution. Let you 2 minus 1 2 and V1 0 1 be two vectors. Let's compute at first. That's the first question. Compute u dot v, the dot product between both, and the angle between them. Second, find the projection of u onto v and the component of u that is orthogonal to v. U dot v is given by the formula modulo of u, or the size of u, multiplied by the size of v, multiplied by cosine theta, which here is the unknown. This is what we're looking for. Modulo of u is equal to the square root of x squared plus y squared plus z squared of u, or square root of 2 squared plus minus 1 squared plus 2 squared equals square root of 9, because you have 4 plus 4 8 plus 1 9 equal 3. V, the modulo of v, is given by the square root of 1 squared plus 0 squared plus 1 squared equals square root of 2, and u dot v is equal to, we multiply element by element both of the vectors, so it is 2 times 1 plus minus 1 times 0, which is 0, plus 2 times 1 equal to 4. So now we can evaluate cosine theta, which is u dot v divided by u, or modulo or scalar of u, not scalar, okay, the size of u multiplied by the size of v. So cosine theta is equal to 4 divided by 3 square root of 2. Hence, theta is equal to cosine, arc cosine, okay? So it is the angle for which the cosine is equal to 4 divided by 3 square root of 2. This is the meaning of it. So theta is equal to cosine minus 1, or arc cosine of 4 divided by 3 square root of 2, which is 19.47 degrees. So the angle is 19.47 degrees, and the product, like the dot product, is equal to 4. B section, which is the projection of u onto v. Projection of u onto v is given by, and you remember the formula, this is u dot v divided by v dot v multiplied by v, which is equal, okay, u dot v, it is 2 plus 0 plus 2 divided by v dot v, which is 1 square plus 0 square plus 1 square, okay, multiplied by u multiplied by v, pardon me, okay, which is 101. It is equal to 4 divided by 2, which is 2 multiplied by 101, or 202. Orthogonal component of u, or residue, is given by u minus the projection of u onto v. So it is given by u is 2 minus 1 2 minus the projection of u onto v, which we've gotten moments ago, which is 202. So it gives us, and you subtract element by element, this gives us 0 minus 1 0. Okay, so 0 minus 1 0, if we multiply it by v, which is the second vector, it should verify the orthogonality. So 0 minus 1 0 dot product v, which is 101, is equal to 0 minus 1 0 times 101. So it gives us 0 plus 0 plus 0, which is 0. This verifies the orthogonality. Another exercise, let S be equal to the span of A1, A2, with A1 equal 1 to 2, A2 equal to 1 minus 1 in R3. Find the projection of B onto S, and the residual R equal B minus projection of B over S for B 3 3 0. Okay, so A is equal to 1 2 2 2 1 minus 1, which are respectively the first and second vector that will form these two columns within the A matrix. And B is given by 3 3 0. So the projection of B over S is given by this formula, which I'm sorry to tell you, we need to memorize it in case you need it. So it's given by A multiplied by transpose of A times A inverted. So A multiplied by the inverse of transpose of A times A multiplied by the transpose of A and multiplied by B. Okay, so transpose of A times A, which is 1 to 2 to 1 minus 1, multiplied by, you flip it over, okay? Actually, yeah, this is the flip over, so the column had become the row. You have 1 to 2 here, and 2, 1 minus 1 becomes 2, 1 minus 1. You multiply them together, you get a matrix of 2 rows and 2 columns, which is 9, 2, 2, 6. Now, the inverse for that is equal to 1 divided by the determinant, which is 54 minus 4, or 50, multiplied by, you flip 9 and 6, so you get 6 and 9, and you multiply this diagonal by minus, so this is the inverse, okay? Then you multiply it back by A from behind, okay, then ATB, so we get, okay, A1B is equal to 1, 2, 2, 3, 3, 0 equal 9, A2B, which is A2 multiplied by B is equal to 1 minus 1 multiplied by B, which is 3, 3, 0, okay, so this is ATB we are evaluating here, so it's A1 times B, okay, yeah, 1, 2, 2 times 3, 3, 0, because remember this was the column, it became the line, correct? So this is AT here, let me highlight it, so AT is given by these two rows, 1, 2, 2, 2, 1, minus 1, and we are multiplying it by B, which is 3, 3, 0, okay? For A1, okay, so A1, this is A1 here, 1 to 2, multiplied by B, it gives you 9, and A2, which is the second line in the transpose, multiplied by B, again, B is 3, 3, 0, it gives you 9. Okay, so AT times B is equal to 9, 9. All right, now we've gotten AT times B, which is 9, 9. We've evaluated also the inverse of the transpose of A multiplied by A. We still need to multiply it by A from behind and then multiplied by ATB, which we've gotten already. So ATA minus 1 is 1 divided by 50, 6, 9 minus 2 minus 2. We obtained that result already. So C is equal to ATA minus 1 times ATB. Okay, that is without the A from behind. We multiply them, you get 18 divided by 25 and 63 divided by 50. Okay, then we still need to multiply them by A. Okay, so projection of B over S is C1A1 plus C2A2, which is simply, yeah, this is 18 over 25, like another way to write it, lest it confuses you. So it is 1, 2, 2, 2, 1, minus 1, multiplied by 18, 25, 63, 50. Okay, so you have 1 times this one, then 2 times the second, okay, then 2, okay, you get the point. So it is C1A1 plus C2A2. A1 is 1 to 2 here, and A2 is the second column. You can multiply them using A as a matrix and placing next to it 18 divided by 25 and 63 divided by 50. You will get the same result. So 1, 2, 2. This is the A matrix. 2, 1 minus 1 multiplied by 18 divided by 25 and 63 divided by 50. So the projection of B over S is given by, you get 3 elements, of course, 81 divided by 25, 27 divided by 10, 9 divided by 50, approximately 3.24, 2.7, 0.18. So this is the final answer. As for the residue, R equal B minus the projection of B over S, so which is 330 minus the projection equals 3 minus 81 divided by 25, 3 minus 27 divided by 10, the result, like the vector we obtained moments ago, and 0 minus 9 divided by 50, so it is minus 6 divided by 25, 3 divided by 10, minus 9 divided by 50. You can check the orthogonality and definitely it will get you the final result.